pleasure to give a talk about the DsTau experiment, which studied tau neutrino production with nuclear emulsion at CERN SPS. Tau neutrino is one of the least studied particles. There are only few measurements do not register tau neutrino directly in the beam, and there are some other experiments which registered oscillated tau neutrinos. The cross-section is known with a large error, more than 50%, which caused by systematic uncertainty in tau neutrino production. The precise knowledge of tau neutrino cross-section will allow to test lepton universality. Here is schematic view of tau neutrino cross-section measurement with the accelerator. We are interested in this part when high energy proton interact with the target and tau neutrinos are produced. The main source of this such a decay when proton interact, ds appears, and it decay to tau and neutrino, and tau decay as well. As it's clear from the name of our experiment, we are interested in these interactions. The goals of our experiment, first of all, study of tau neutrino production for future tau neutrino experiments, which include the first measurement of DsTau differential production cross-section. And we are planning to provide tau neutrino production with a beam dump method at the range of about 10 GeV, and to reduce uncertainty of tau neutrino flux from more than 50% to 10%. Also, charm physics topic is interesting itself. For example, intrinsic charm component study. As I said, we are planning to detect such topologies of so-called double kink, where ds decay to tau, accompanied with a pair charm decay. The registration of this topology is quite difficult because the range of these decays is about few millimeters, and the kink between this and tau is quite small. It's just few milliradians. This challenging task can be performed with the emulsion detector. For example, we use emulsion, which has a spatial resolution about 50 nanometers and angular resolution about 0.35 milliradians. Here is a schematic view of our detector. This is a basic unit. It's a tungsten plate followed by 10 emulsion plates interleaved with 9 plastic plates. Detector consists of 10 such basic units. There is a proton tagger in the upstream part, which is just 5 emulsion plates with 4 plastic plates, and so-called emulsion cloud chamber, which used for momentum measurement. Here you can see a picture from our pilot run. This is a size of our detector, 10 centimeters by 12.5 by 8.6 centimeters. It's installed on the target mover, and we have a signal from other detectors which count proton beams, and target mover, according to this signal, move detector in such a way we have a smooth intensity of protons along the whole detector plate. So we look for such a signal. DsTau decays accompanied with decay of charged or neutral charm. Efficiency to detect such a process is estimated with PFA8, it's about 20%. Thus, in total, we expect about 1,000 of such events to be registered. The main background comes from secondary hadron interactions where nuclear fragments are not registered, and we expect to have about 18 background events for our statistics. We already had two test beams and a pilot run in 2018, where we collect about 10% of full-scale experiment statistics. In principle, these statistics already allow to reduce flux uncertainty till 30% percent and to revise donut results, and also to study charm physics. After pilot run, our experiment was approved as NA65, and now we are preparing to physics run in this year and the next year. In this year, the physics run will start in the end of September. Actually, we planned to expose about 250 square meters of emulsion, but due to COVID situation, we will be able to expose about 100 meters and to increase the number of um, our emulsion in the next year. Here you can see the emulsion production. On the left, there is a manual production facilities in Nagoya and Bern. Emulsion was poured by shifters on two sides of plastic base, and the speed of such production was about 5 or 7 square meters per week. Now for a physics run, we're using automated production line in Nagoya University with a speed of production more than 10 square meters per day. Also, we are working on geometry improvement. So we prepared a target mover which able to move a larger detector, and we will increase detector size. This will allow to speed up scanning, since the main time during scanning is spent by shifter for changing emulsion plates on the scanning station, not for the scanning itself. And also we will replace ECC with 2.5 basic units, because it easy to process, and it will be enough for reconstruction of particle momentum as well. Our analysis is go in two steps. First step is fast full area scanning using hypertrack selector in Nagoya. It recognizes track segments in each emulsion, and then track reconstruction goes offline. The angular resolution of this station is about 2 milliradians. So if kink between ds and tau is smaller or comparable with the resolution, we cannot find it in this first step. And so we are looking also for such topologies where there are only two decays. And then we have a second step of analysis. We take these preselected events and look for kink inside these tracks which are candidates to charm. The angular resolution of this scanning station is about 0.3 milliradians. During exposure, we collect about 10 to 5 primary protons per square centimeters, and here you can see the track density along our detector. This is a view of 2 by 2 square millimeters subvolume of our data. Although the track density is so high, the tracking efficiency is still quite high. It dropped a bit with the plate number, but still keeping more than 94%, which is enough for our goals. Alignment between plates is done with the passing through protons. Here is an example of vertices reconstructed in tungsten plate. The vertex density is about 400 density per square centimeter in one plate. The distribution of vertices along that position reflect the structure of our detector. It's higher in tungsten plate. And we are working on a comparison of the data with the several Monte Carlo generators. Here, for example, you can see comparison of primary vertex charge particle multiplicities with Fluka. So we analyzed subsample and select their double charm events. The number of found vertices and selected double decay topologies in the data is in agreement with the expected numbers. And here is a Monte Carlo flight length of charged and neutral charm candidates between data and Fluka. Here you can see the example of one of double decay topology candidates. Charge track has a kink, and here is a candidate to be a decay of neutral charm. This small sample was used to tune parameters for kink search and neutral charm with two-pronged topology search. And after this, the mass processing with the efficiency improved cuts has been started. Now we analyzed about 22% of pilot run data. More detailed analysis will be done for double decay topology candidate sample. Some algorithms of detailed analysis still to be tuned, while others can be applied systematically already now. And here is an example of selected double kink candidate. Here is a proton interaction. This is a double kink and pair charm candidate. And here is a zoom of this double kink candidate. I remind that each segment corresponds to a piece of track in one emulsion layer. To summarize my talk, I would say that DsTau project was proposed at CERN SPS to study new tau production and was approved as NA65 2 years ago. We are aiming to detect 1,000 of DsTau decays in 400 GeV proton interaction using emulsion detector. We are planning to reduce systematic uncertainty in the new tau cross-section measurement from more than 50% to 10%, and to study charm particle production. We successfully performed a pilot run in 2018 and collected about 10% of the data. Analysis is ongoing. We completed the fast full area scanning and started mass production, which is completed on about 20%, up to the level of double kink topology candidate search. The Ratha data analysis is ongoing. Also, we are preparing for physics run, which will start about in 1 month. We are optimizing detector geometry, and we produced emulsion with a high-speed automated production line. And also we are preparing fast readout for analysis of physics run data. Thank you for attention.